In this lecture, we will describe the Corona publish subscribe system. So this is an extension of what we have been studying in the distributed with regards to distributed hash tables. Particularly, this is an extension of pastry. So we will see how to use it in this setting. So first, we will describe the general structure of publish subscribe systems. Then we will discuss the design of Corona. And finally, we will discuss the results, the evaluation results of Corona. So let's first describe the broad structure of a publish subscribe system. So the broad structure is like this. So in any publish subscribe system, we have a set of publishers and we have a set of subscribers. So let us say that this is a hypothetical space. So all of the publishers publish topics of interest, publish stories of interest to the pub sub system. So what could this be? Well, this could be something like this. That so consider the stock market. So if I am a broker, I might be interested in, let's say, the stocks of 5 different companies. So then, whenever the stock of any company changes, so some dedicated server can just publish the updates to a pub sub system. There might be a set of subscribers who would be interested in a subset of the stocks. So the moment that there is a change, a message will go from the pub sub system to the subscribers, right? Whichever subscriber is interested, telling them that look, there is a change, there is an update. So in the case of a stock market, one of the stocks that you were interested in, that stock has changed. So you would like to take a look at the new stock price. So in general, what happens for subscribers is that they express interest in certain topics. So this is notified to the pub sub system. Similarly, the publishers also they first register with the pub sub system, and then they publish their updates. So this can be anything. These can be stock feeds, stock prices. These can be news feeds. So it can be anything. So if you would see, one of the most common pub sub systems is called an RSS system. So RSS or Atom. So you would see RSS or Atom links with popular news websites. So in this case, what can happen is that I can take RSS feed reader like aggregator, for example, and then whenever there is an RSS update, that will be shown to me, right? So whenever there is a new news story, that will be shown to me. So I'm showing you the RSS page of Times of India. It's a very popular newspaper in India. So if you see, so the Times of India is publishing stories with respect to many topics. So top stories, India, world, business, cricket. So if I want, I can subscribe to many of these topics. The moment that there is a new story in, let's say, for example, science, I will have a dedicated RSS feed reader, and the dedicated RSS feed reader will show me the update in science. So let me click cricket, for example. So what you see over here is a complicated, unreadable piece of text. But if I were to open the same in an RSS feed reader, then actually I would nicely see all of the updates in my feed reader, right? And so a quick word about RSS. If I were to show you the Wikipedia entry, so RSS, the full form is really simple syndication, and so this gives us summaries of websites where it's one of the most popular pub sub systems. The websites publish their news, and then we can subscribe to them, and then I'll immediately get notified the moment that there is a change in a website. So pub sub systems are not just limited to RSS, even though RSS is very common. uh, Pub sub systems are kind of there everywhere, where we have a publisher that posts updates, and we have a subscriber that registers to get updates. So we just saw a example of RSS, but of course this can be in any kind of a system. So how does this actually work? So the way that this actually works is kind of interesting. Let's go back to our journal over here. So the way that this works, well, we can have two methods. The first is polling. So in polling, what happens is that the subscribers keep on asking the publisher, do you have an update? Do you have an update, right? And the other is kind of an interrupt driven mechanism, where the subscriber registers her IP address with the pub subsystem, and whenever there is a change, the subscriber is notified. So clearly, in an interrupt driven system, the pub subsystem has to do the work. It has to maintain state. Whereas in a polling based system, the pub subsystem does not maintain any state. So the specific motivation for Corona is like this, that a polling based methods are not very efficient because they place a lot of load on the server. So Corona provides a very scalable method and very flexible method also to disseminate updates. So let's say, for example, I'm interested in updates, sports updates, and let's say there are a million people like me. So all million of us should not actually be polling the sports site and actually trying to get updates. And also, so let me draw this over here. So let's say there is a sports site, a website, and there are millions of subscribers. So we have discussed two methods, polling and interrupt based. So in the polling based method, the millions of subscribers go to the site and keep seeing if there is some new news or that there is some change. And clearly this increases the load on the site. So most cricket lovers would actually go to the site Cricinfo whenever a match is going on and we can't actually see the match. And pretty much we keep on pinging it to see if, if there is a new status update. And the other is that actually the server essentially notifies the update to every browser. It maintains state. So in that case, if the state changes, then each of the client browsers needs to be notified. So this also places a large load on the server. So the main aim of Corona is to place a degree of intermediaries over here, which minimize the load on the server as well as stop the clients from polling, right? So the intermediaries actually poll the server, but they minimize the load at the server. And instead of the clients polling, they actually send messages to the clients whenever there is an update. So the intermediaries maintain state. So what is Corona once again? Well, if there is a very popular website and there are a set of clients, let's say lot of clients, then Corona is kind of like a middleman sitting over here, where the Corona, where each of the Corona nodes maintains state, so it keeps track of the clients. Whenever there is an update, it disseminates the updates to the client, and the nodes themselves keep polling the website, but they do it in such a way to minimize the load on the website. So the website is happy. The intermediate layer, which is Corona, that we need to study. And of course, the clients are happy because they quickly get the updates without increasing the load at the server, because otherwise the server will crash. So this is the basic idea, the core idea of having a kind of a middle layer, some kind of an intermediate layer in a traditional pub sub system. So what is pub sub used for? Well, it is used for content that changes frequently and for which we need to quickly know that the content has changed. So these could be blogs, Wikipedia, news sites, but most common it is like news. I would say that's the most common. Stock prices, that's also very common. So sports scores, updates, right? Cricket, for example, right? All day, if a match goes on for the entire day, we are getting updates. So the current solution is using RSS feeds, as I just showed you on Times of India's website. It's called micro news syndication, and it's kind of based. So now there are many more sites that also give us short news briefs. So many of these sites like InShots and so on give us very short news briefs. But all of these are based on very simple polling. So there is clearly a trade-off between the latency perceived at the client and the bandwidth at the server. So both need to be taken care of. So one is minimize the server load. The other is latency of updates. So the idea here is that the load at the server, of course, has to be minimized, but also the latency of updates for each client, even that also has to be reduced. So what are the contemporary approaches? The contemporary approaches is that some content providers impose a rate limit on the amount of bandwidth per IP address, the number of IP addresses that can connect at the same time, or a range of IP addresses. So servers can also ask the client to stop polling or change their polling intervals. So that is why many of the popular news sites like including Times of India or anything else that has a large viewership, so actually they go via intermediaries. So one of the most popular intermediaries is actually a provider called Akamai. So what Akamai does is that it essentially sits between some very popular websites and the clients. So whenever a client browser actually points to some very popular website, it essentially hits an Akamai node, and it's the job of the Akamai node to collect updates from these websites and give it to the client browsers. So of course this process is hidden from us. So as a client browser, we don't get to see it, but it is kind of still happening. Akamai, which sits in the middle, that actually does it for us, right? Which is that getting the updates, latest updates from the server and giving them to the clients. So Corona's aim is something very similar. So of course, Akamai is a proprietary solution. Corona is in academia. So it manages a server's bandwidth efficiently, stays within limits, and gives the clients the best possible update latency. So of course, for clients, uh, you can think of this as something which can either be polling or interrupt. But the relationship between a content aggregator or a provider like Akamai or Corona and the website is a purely polling based relationship. So how did the Corona system, which was done way back in the 90s, how did that actually work? So users subscribed by sending instant messages to a registered Corona user ID. So of course, instant messages are there everywhere. So we have, we have a lot of instant messaging protocols like Google Talk and so on, right? Skype and Google, and we have a lot of instant messaging platforms. Also, we have the software called Game in Linux, which kind of aggregates all of them. So they send an instant message to a Corona user ID. Corona is a set of nodes on the cloud that monitor a set of channels. So essentially, every website or every content provider is called a channel. So essentially, any service that generates an active feed of data, an active feed of news is called a channel. So the Corona resource allocation algorithm will essentially dedicate a set of nodes in Corona to monitor a given channel. So they will do that. So they will filter out useless content. So this can include timestamps and advertisements and things that actually clients don't need. And then a difference engine will extract the relevant portions that have changed. And these differences will be distributed. The new updates will be distributed to the clients. So this is all that Corona does, which means it first does polling, it polls the channel, it extracts the difference, and then it distributes the difference to the clients. So the motivation now, we are kind of well motivated. So let's look at a few of the solutions in related work. So the solutions in related work go something like this. We have publishers who post the content. We have subscribers who subscribe to relevant content, and so this process of subscribing to relevant content can be done in two ways. One can be topic based, which means that publishers and subscribers are essentially connected by a set of topics, and each topic is a channel. So the topic, for example, can be food. So whenever there is any update on food, it is given to the clients. So this is not exactly how Corona works. So Corona is content based, where subscribers uh, can make queries on the, well, let me take back my statement. So Corona is actually channel based, and so in this case the channel is like a specific website or a specific provider. So a topic of course can span across channels, in the sense multiple websites can be providing food. So this is not exactly what Corona does. It's a single channel. It's kind of a subset of topic based. Content based is again when we make queries on the content. So the content is not organized by topics, but it's just like raw content. And then we essentially ask Corona to go through all the content and find the relevant ones that need to be sent to the clients. So content based is not something that Corona does. So what it does is actually a subset of a topic based pub sub, where we get updates from a particular channel. So many of the research prototype pub sub systems require custom interfaces, and they are difficult to use. So one great advantage of Corona was that it is kind of compatible with all content providers. and it is rather easy to use. It is based on instant messaging. Instant messaging is ubiquitous. It is available everywhere, and because of that, uh, the Corona system is extremely popular. So we have already discussed RSS. What is it? It is short updates of frequently changing data. So can be news stories, blogs, blog posts. So they typically use an XML based format to share very short updates, and we can access it via HTTP over standard URLs as we just saw. And there are dedicated RSS feed readers like aggregator to display the data. So then the server informs the client when to poll and when not to poll by using a certain tag called a cloud XML tag. So the servers in RSS automatically do some sort of a rate control. And if let's say there is excessive polling, excessive load at the servers control the rate. But in the case of Corona, this is not required. So an example of an RSS XML snippet. So the first mentions the version of XML, the version of text encoding, the RSS version 2. So this is a channel. So the channel of course can have a lot of things. So in this case, let's say I updated my home page. So then, so my home page will come here along with the link that has been updated, the description of my home page, and the particular items that have been updated. So let's say I updated my teaching page and I updated my research page. So both the updates, right? So let's say I just change the descriptions, for example. So both the updates, the update for the teaching as well as the update for the research, both of them are showing up over here. All right. Both of them, the update for teaching and research, show up as separate items in the RSS link, right, in the RSS snippet, and a dedicated RSS feed reader uh, displays these items to the reader. Now that we come to the design of Corona. So Corona stands for Cornell Online News Aggregator because this was initially a project from the Cornell University. The key features of Corona are as follows. The first is cooperative polling, which means we assign multiple nodes to poll the same channel and share updates. So if this is the same channel, and we have multiple nodes, then they poll the same channel and they share the updates with a much wider base of clients. And of course, the number of nodes that we assign to poll the same channel depends on the popularity of the channel, the nature of the content, the size of the content, and how many clients are interested. So this is posed as a global optimization problem, and the honeycomb optimization toolkit is used to actually solve it. Corona uses a pastry based overlay. So recall that in pastry what we were doing is that we had created a large circular space and we represented numbers in a given base. So the first thing that we actually did, so consider a channel. So for each channel, let's say a channel is uniquely identified by its URL. So from the URL using the SHA algorithm, we hashed it. We produced a hash value. So the hash value was not exactly represented in binary, but it was represented in base B. So recall a small clarification over here In the pastry paper, actually the base is 2 to the power b, but in the corona paper, it's not 2 to the power b. The convention is that the base is b. So we'll go with this convention, the corona convention. Even though recall that in the pastry paper, the connotation of b was actually different, and the actual base was 2 raised to the power b. But as I said, in corona, we will go with the convention that the base in which the hash is being represented is in base b. So this hash is in base b, and for every such hash value, we can find a position for it in the ring. So the channel can be positioned over here. So it is expected that uh, the match that it will have. So the nearest node, right? So the idea here also is the same, that the closest node with the channel, that is the owner of the channel, right? And it is expected that the level of the match will be log n to the base b, right? So that is the expected value. So if it doesn't happen, of course, we'll see what is done, but this is expected to be the common case. So what corona actually does is that it defines a wedge around the channel, something like this, something like a pizza slice. So which means it logically splits the nodes on this. So what it does is that for the circular ring, similar to pastry, it maps both the nodes as well as the channels. The channel's URL is hashed and mapped to the ring, and for the nodes, the IP address is hashed and mapped to the ring. So once all the nodes and channels find a place on the ring, we can define a wedge, where a wedge is defined as a set of nodes that share a common number of prefix digits with the channel's identifier. Alright. So if a channel has polling level L, this means that it is polled by all the nodes that have at least L matching prefix digits with it. So let's explain this in some more detail, because this is by far the most important concept in corona. So both the channels as well as the nodes are mapped to this circle. So let's say that the channel is mapped over here. So then one of the nodes will be the closest to the channel. So this node is made the owner of the channel. So let's say it's this node over here. So this node is the owner of the channel. So it is expected that the degree of the prefix match will be log n to the base b. So of course, if it doesn't happen, we still find the closest owner and we reduce the prefix match. Now what we do is that around each channel we define a wedge. So every wedge, so a wedge is like a pizza slice. So with every edge we define a polling level L. So the polling level L basically means that there are L matching So there are L matching prefix digits with the channel ID. So let's say that the channel ID we are representing in base 16. So it would be something like, so let's say something like this. And let's assume by prefix we mean from left to right. So if this is the channel, then for a given node, if let's say it is a part of the wedge that is monitoring the channel, so I'll come back to what is monitoring the channel, but let's look at this for the time being, and let's say it diverges from here on. So in this case, the polling level is equal to the number of matching prefix digits. In this case, the number of matching prefix digits is 5. So the polling level is 5. So we can always define a wedge based on the polling level. Lower is the polling level, the wider is the wedge. Higher is the polling level, the narrower is the wedge. And of course, once the polling level crosses log n to the base b, we expect the size of the wedge to be 0. So at the beginning, the size of the wedge will just contain just the node and the channel. And then the polling level is expected to be log n to the base b. But of course, if the channel is very popular, we would like a lot of nodes to poll for the channel. So what we actually do is we partition the hash space in pastry by defining a wide wedge. How do we do this? By reducing the polling level such that we have a wide wedge over here. And the magic of Corona comes right here, that all the nodes within this edge poll for the channel. So what is the magic of Corona? Well, the magic of Corona, the key idea is that all the nodes is that all the nodes in a wedge poll the channel. So if we just want more nodes to poll the channel, well, all that we have to do is that we have to reduce the polling level. Once we reduce the polling level, we will have more nodes that it will span, and the increased number of nodes will actually come and poll the channel. And let's say the channel loses popularity, then all that we need to do is that we need to increase the polling level, the wedge will shrink. So let's say the wedge might become something like this. And then a fewer number of nodes will poll the channel. So on a similar line, we can have different channels at different parts of the pastry ring. For each of them, we will have a wedge that is defined. Also note that in this case, wedges can be overlapping. So in this case, let's say if there is another channel over here, let's say something like this, we can have, let me use a different color. Let's see if I can do that. Pen settings. Yeah, I can. So let's say there's another channel over here, which is this channel. Then essentially I can define a wedge for it, which would look something like this. So here kindly note that the two wedges are overlapping. So nodes in the overlapping wedges would actually poll for both. So Corona does have a way of managing such conflicts in a very indirect manner, but we will discuss that later. As long as the key concept is clear, and the key concept over here is the concept of wedges, which are essentially partitions of the hash space. Right, so the concept of wedges is the most important, and it is essentially a partition of a hash space, and that is clearly the most important concept here, that we can either have a wide wedge or a narrow wedge depending on the polling level, which can be changed dynamically. So the entire optimization problem within Corona, in Corona, the entire optimization problem is to essentially figure out the wedge sizes for each channel. So that would talk about the server load, that would talk about the load on the Corona nodes, and that would also determine the update latency of the client. So all of this is related to the wedge size. Well, how? So if the wedge size, if the wedges are very wide, this will mean that we are getting a lot of updates from the server, the update latency will be low. So I can maybe summarize this over here. Let's say a wide wedge. Low update latency because a lot of nodes are polling, and they can also poll at random intervals. So with that, what will happen is that if there is any change, it will quickly get caught by one of the nodes in the wedge, it can then distribute the updates to the rest of the nodes. So a wide wedge will have a low update latency and a high server load, and vice versa, a narrow wedge will have a high update latency and a low server load. So we need to find this, and we need to, so there are conflicting requirements of the update latency and server load. So we will see how Corona solves it. Alright, so we understood the notion of a wedge. There's a common number of prefix digits. A channel has polling level L if it is polled by all the nodes with L matching prefix digits with it, which means all the nodes within the wedge. So a little bit of math over here, let the total number of nodes be n. A channel with polling level L will have on an average n by b raised to the power L nodes in its wedge. So I'm not proving this, instead I'm directing the viewers to the pastry paper that proves this in great detail. So this paper has to be read as a prerequisite before looking at, before viewing this lecture. So we will assume that this is the kind of a gospel truth here. Sorry, this should be tau. So let tau be the polling interval. So the average detection time for updates. So the average detection time. So if let's say we call it the so let's give it this name, det time. So the det time is clearly proportional to the reciprocal of this, or inversely proportional to the number of nodes in a wedge. Higher are the number of nodes in the wedge, so assuming that they are polling at random intervals, which is the case, the detection time will be inversely proportional to it. So we can say it is b raised to the power L divided by n. Furthermore, the detection time will also be proportional to the average polling interval, right? Which means that for every server, if it is polling once every tau seconds, the detection time will be proportional to that. And in addition, given the uniform distribution that we are assuming here, which means that let's say that if a server is polling and between time 0 and tau it could have been changed, the data could have changed at any point in time, the average latency will be tau by 2, which is easy to prove. So this gives us the average detection time for updates to be tau by 2 times b to the power L by n. And the collective load placed on the server is clearly proportional to the size of the wedge, which is n by b to the power L. So the problem is to estimate the polling levels of each channel, or alternatively the sizes of the wedges. So let us now discuss a few of the Corona schemes. So the first is Corona Lite, which is also the first scheme that comes to our mind when we think about this problem intuitively. This ensures good update performance while ensuring that the load on the servers is light. So let's first look at the terminology. Let M be the number of channels, Qi be the number of clients for channel I, right? So this is important. Q is for number of clients for channel I. Li is the polling level of channel I, N is the total number of nodes, and Si is the content size for channel I, of course appropriately normalized. This is important, and this is not something that the paper stresses on, but it's important for me to stress that it has to be appropriately normalized. So it's a normalized content size for channel I. So what are we trying to do here? Well, what we are trying to do is that we are trying to minimize Qi times b to the power Li by n. So let's see what this is. So b to the power Li by n, let's just go to the previous slide. So this is proportional to the update time, the update detection time. It is proportional to this quantity. So we say that this is the update detection time. And this we are kind of weighting with the number of clients for channel I, right? And so moment we want to minimize this quantity, which is the weighted sum of the update detection time, Let me repeat that. This quantity is the weighted sum of the update detection time, where the weight is the number of clients for channel I. We want to minimize that. So what effect will this have? Well, the effect that this will have is that for any channel that has a large number of clients, we would like to minimize the update time as much as possible. So essentially for popular channels, we want to deliver updates as quickly as possible. And we essentially want to penalize less popular channels. So this is of course the objective function. What is the constraint? The constraint is, so n by b to the power, sorry, I should delete that. N by b to the power li, which is the same as this quantity over here, is essentially the expected size of the wedge. So this is the expected size of the wedge, and this is the size of the content of the channel. So if I multiply the content with the size of the wedge, this gives me an idea of the bandwidth, right? The bandwidth requirement from the server to kind of supply data to all the Corona nodes. So this is an estimate of the bandwidth of the server. So if I were to add up the collective bandwidth of all the servers, right, for all the channels, so the collective bandwidth for all the channels has to be less than equal to the number of clients, and this is like kind of a bandwidth constraint. The reason that this is a bandwidth constraint is that, look, if this was equal to the number of clients, we didn't need Corona. So one main advantage of Corona is that we want to pretty much reduce the bandwidth requirement at the server, right? Because otherwise the server could just provide data to all the clients. We didn't need Corona in the first place, right? So we keep this as a constraint, that the normalized content size multiplied of course with the size of the wedges, the sum of that across the channels should be less than equal to the total number of clients for all the channels, which if you see from a common sense point of view also makes sense, because this kind of justifies Corona, right? If we didn't have this, then pretty much, Corona, what would happen is that in the quest of minimizing the update time, the bandwidth requirement from all the servers would be more than what a non-Corona system would require, which would not make any sense at all. So given this kind of a common sense constraint, we try to minimize the update time. So here what happens is that the clients of popular channels, needless to say, gain a lot, because for them the average update time gets reduced, that too significantly. This nicely partitions the bandwidth across the channels. The update performance of course would vary depending upon the type of the workload, because the type of the workload is not being considered here very explicitly, and for less popular channels they kind of suffer in this case. So then we define Corona fast, which is expected to be the fastest. So I'll explain in a second why. The terminology remains the same, where M is the number of channels, Qi is the number of clients for channel I, Li is the polling level of channel I, N is the total number of nodes, Si is the content size, and T is a certain constant. It's a performance target. So what am I trying to do over here? I'm trying to minimize this quantity. What is this quantity? So Si is the, so this quantity is exactly the same as this quantity. In this case, Si is the content size, as I said, normalized, multiplied by the size of the wedge. So in this case, what I'm trying to do is I'm trying to minimize the bandwidth, the load placed on the content servers. I'm trying to minimize that. Subject to, so this is interesting, this quantity is the same as this for Corona Light, which is the This is the weighted update time. So this is essentially the update time weighted by the number of clients. So we want to keep the update time less than a certain threshold. So there are two uh, aspects to this threshold. One is a constant, and the other is the total number of clients. So of course, the update time should be a function of the total number of clients, because as the number of clients increase, what that would essentially do is that would place a higher load. And here what we are saying is that, look, if the total number of clients are increasing, then the system is expected to be less responsive. The update time should increase, and that's kind of getting captured over here. And T is just a factor for normalization. But the key aim over here is that, look, I want to achieve a target update time. And the target update time is should be less than a threshold. And the threshold is proportional to the total number of clients across all the channels, which also it should be. That if there are less clients, I should expect a lower update time. And if there are a lot of clients, I should expect a larger update time. So Corona Fast is clearly the fastest when it comes to update time. Now the question is why? So an astute reader can always ask that, look, for Corona Lite, you try to explicitly minimize the update time, whereas in Corona Fast, you try to minimize the bandwidth. So from a common sense point of view, Corona Lite should give the fastest update time and Corona Fast should not. Well, that's true, but that's not the case. In this case, we are like kind of forcing the update time to be less than a certain value. So this is like a knob which is totally under our control, and we are turning the knob to a point where our update time is the lowest possible time that is possible. And in this case, the bandwidth is kind of going free. So we are trying to minimize it, but think of the update time as being constrained and the bandwidth as being free. So we can lower this as much as we can, to achieve kind of any target within a feasible range. And once we have kind of set up our mind on this, then we can, of course, so once we set up this threshold over here, which is the constant T, which is the most important, that sets our target. Once the target has been set, we minimize the bandwidth. So clearly this is totally in our hands. We can make Corona as fast as possible. Whereas in this case, the target is the bandwidth, and then of course our space for reducing the update time is kind of constrained. That's why Corona Fast, as the name suggests, is genuinely faster in terms of update time as compared to Corona Lite. I would ask the viewers to go over this logic several times till they are convinced. So this of course bounds the total amount of network traffic, that it does. Uh, well, it doesn't bound. If you would actually see, it actually tries to minimize. So I should maybe change this. It allows us to tune the update performance per application, which is just what I said. Given an application, we can fix a target. For example, for a stock market application, we might choose a very fast update performance. So along with providing application the desired level of update performance, it tries to shield web servers from spikes in load by reducing the bandwidth. So of course, the negative aspects for both of these protocols is that both Corona Lite as well as Corona Fast do not consider the rate of change of objects in a channel, in a sense that, look, the update time only makes sense in the context of the rate of change of the object. See, the object is not changing, there is no point in actually polling the channel. So Corona Fair takes this into account. So it introduces a few additional variables. So recall that this structure Qi, B and N is similar to Corona Lite, Qi, B and N. So this is kind of Corona Lite plus plus, where this is the normalized update time Qi, B, Li, N multiplied with tau, which is the polling interval, this should have been there. And also the polling interval can be different for different channels. So this, of course, this variant of corona does not consider, but this is something which can be considered. And the other is the update interval for channel I, because for different channels, the update intervals will be different. For example, for stock prices, the update interval will be low, particularly when trading is happening. Some stocks will be changing very quickly. But once the uh, stock market has closed for the day, the update interval will actually be very high, right? Because the stock prices are not going to change. The stock prices will only change when the market reopens. So any kind of a corona polling should take this into account, and the rate of change of the content is what is coming up over here, right? So let us say that the rate of change is very high, then UI will be low, so this constant will be high. If this constant will be high, then essentially we want to minimize the update time. But let us say that we have a very slowly changing channel. UI will be high, this uh, fraction will have a low value. So then of course we can afford to have a high update time for the channel. And this is our regular bandwidth constraint which we had in Corona Lite if I were to show you. So it's the same constant that we had over here, which is what we have over here. So this remains the same. The only addition is the update interval. So we are using two terms here, update interval and update time. So update interval is a property of the channel and the channel only. So this is UI, and the update time is a time that a client perceives between the actual update to the channel happening and the client actually seeing it. That's the update time, right? So the update time, recall, keep in mind, is a different concept, and it is what is perceived by the client. So of course it can be, so one criticism of this formula is that for very slowly changing channels, the update time can be very large, which is kind of unfair, right? So we are basically giving too much importance to UI. To kind of reduce the importance in UI, what so two other variants of corona, what they do is fair square root actually considers the square root of this quantity to kind of temper down the effects of UI. And if we further want to temper down the effects of UI, instead of the square root, we consider the log. So that will further kind of reduce the effects of a large or small UI. And so we consider the ratios of the logs. So as we discussed, Corona Fair is similar to Corona Lite. Corona Fair, of course, has two versions, Fair Square Root and Corona Log. It also tries to minimize the update detection time, which we call the update time in the lecture. So recall, update time is different from update interval. Just go back to 2 slides back. So it minimizes the weighted update detection time with a limit on the total amount of traffic. It also introduces a term to reduce the number of allocated servers if the rate of updates is small, which we have been calling as the update interval. Furthermore, it's possible to dampen this term, right? Dampen by considering the square root, the ratios of the square roots or the logs, as we just saw over here. So this can be posed as a core optimization problem. So the optimization problem in this case will be something like this, that we want to minimize a quantity f subject to some other quantity being lower than a threshold. So these can be kind of expressed as generic functions as f and g, where we want to minimize f subject to g being lower than a threshold. If fi and gi are the performance or the bandwidth cost of the channel at polling level li, right? So it doesn't matter what these are, but for different variants of corona, F and G will be different functions. Then we can set up an optimization problem. And if you would see the corona paper, it proves that the problem is NP hard. But of course, we can find good approximations to it, where M being the number of channels, N being the number of nodes. We can find good approximations within M log N time. Honeycomb can do that. So how does Honeycomb actually do it? Well, Honeycomb, what it does is that it combines channels with similar trade-offs, where the trade-offs are defined as the F and G functions, uh, into a trade-off cluster. Channels with similar behavior are um, nodes and channels with similar behavior are clustered, and the nodes periodically exchange these clusters. And furthermore, nodes locally run the honeycomb algorithm to figure out the assignment of nodes to channels. And of course, disagreement regarding the assignment of nodes to channels can be a problem, but this of course does not happen. But the key idea over here is that there is a distributed mechanism of solving the optimization problem. So it is not that one central site solves it. Instead, what happens is that if, let's say, this is the wedge, each of the nodes individually solves the problem, and each of the nodes individually can on its own volition increase or reduce the polling level. For example, let's say if this node perceives that it needs to reduce its polling level, then what it can do is that it can reduce the polling level on its own volition and consider a bigger part of pastry, right? Bigger part of the pastry ring. Now, some of the systems management issues. So let's just go over the entire process of running the Corona system. So each channel in Corona hashes its contents to get its unique pastry key. This we have seen. It is assigned an owner node the same way that pastry assigns it. For added fault tolerance, a key is assigned to F succeeding nodes. So if you would recall, we had seen something very similar in Amazon Dynamo, where a key is not just assigned to one node, but it is actually assigned to a series of nodes, F successive nodes, such that if one fails, the rest can take over. Owners receive subscriptions and send updates to all the subscribers. So what do the owners do? Owners are the one who receive all the subscriptions, and then they send updates to all the subscribers typically. And also we have cooperative polling, which means that all the nodes within a wedge, they poll cooperatively and share updates among each other. So there are three phases in cooperative polling, and this is cooperative polling as well as independent polling, in the sense that nodes can independently increase or decrease the wedge size. So the first is the optimization phase, where a node applies the honeycomb based optimization technique to the traffic data that it has collected from the servers. So any change to the polling level is connected to is communicated to the peers, and of course nodes can change that on their own. And nodes, and then so this is the maintenance phase, and then the aggregation phase is when nodes receive trade-off data from other peers, so that again they can run the next round of optimization. So initially at the owner node at level k, which is expected to be log n to the base b, polls for the channels. Any node in the maintenance phase, which you would recall is the second phase over here, might decide to reduce the polling level to k-1. In this case, a small wedge will form that will perform cooperative polling. Whenever there is a change in the polling level, some nodes need to be instructed to start or stop polling, which a node will take care. Owners will typically monitor the status of all the nodes in the wedge and aggregate all the maintenance messages, sorry, at the end over here in the aggregation phase. Sorry, yeah. Whenever there is a failure, Corona will remove the nodes from the ring, and on the addition of a node, Corona will add it to the rings the same as pastry. And if let's say the owner fails, then the subscription state of the owner is deleted and a new owner will take over. So Corona in this case, so first I think it is important for me to describe the way that the Corona DAG will form. So the way that it will form is something like this. That if I were to consider the pastry ring, so initially we will have the channel here and just the owner node. So it will be a very narrow wedge. What will happen is, so this will be essentially when the channel is being added. So after that, of course, the servers will be pooled and the node will get an idea of whether it should increase or decrease its polling level in the aggregation and optimization phases. So let's say it decides to increase its polling level. So if it decides to increase its polling level, this is the size of the new wedge. So this means that if the original owner was node O, then it will point to N1, N2 and N3, which are there in its wedge. Here is the interesting part, which might be hard for readers of the pastry and Corona papers to appreciate at the beginning, but this is something that needs to be explained. So what each node actually does in pastry is that it maintains a routing table, and in this routing table, for every prefix, there are a set of nodes that match the next digit. So some of these nodes are kind of kept in the routing table. But the important point to note is that these are not the only nodes that have L prefix digits matching with it. There might be many more nodes, but pastry does not keep a list of all the nodes. So recall that this is the most important point, hence I'm repeating it once again, that let us say that between the ID of the channel, so let's say that these are all the digits in the ID of the channel, and let's say that let us consider all the nodes. So let me first consider the owner node that has, let's say, log n matching bits. And now let us assume that it has reduced the polling level to log n minus 1. So when it reduces the polling level to any L, which in this case is log n minus 1, it will essentially go to a node, it will essentially go to a row in its routing table, where it will basically see that, look, show me all the nodes which have L matching prefix digits, and then depending upon the next digit there will be a set of nodes which will be N1, N2 and N3. But recall that the list is not exhaustive. There might be many more nodes which also have L matching prefix digits, but which don't show up in the routing table, right? Because routing table typically, at least in this case, does not store multiple entries. Now assume that node N2 on its own decides to reduce the polling level to L minus 1. If it does that, it will again point to a set of new nodes which are N4, N5. But given that N1 and N2 also match in the first L digits, they will also match in the first L minus 1 digits. So one of them, and if N1 is showing up in N2's routing table, N2 will also point to N1. And so what we will essentially, and then again N5 might decide to again change its polling level. It might end up pointing to N3 and maybe a few more nodes. So what we will actually have is that we'll have a directed acyclic graph or a DAG. And the reason we'll have a DAG is because the nodes independently choose to either increase or decrease the size of the polling levels. And this is what gives us a directed acyclic graph kind of structure. And the moment N5 or N2 or N1 anybody reduce the polling level, they will cut off edges and vertices from the DAG. So of course we'll have an overall owner, and the overall owner will only know its children, and N2 will know its children, N5 will know its children. So any update that is disseminated by the owner, that pretty much, and of course any node will also know who its parent is in the DAG. So let's say if N7 finds an update, its job is actually to propagate the update all the way up. So there can be different variants of this, but the most common variant would be for N7 to propagate the update all the way up to the final owner. And the final owner will then again disseminate the update to all of the child nodes, so that all the child nodes get the update. So this is pretty much what is being said over here. And of course, if the owner dies, a new owner comes up, it will take control of the DAG and maybe delete the subscription state of the new owner and request for new subscribers. So a lot of things are possible over here. Corona has a dedicated difference engine that computes the difference between different versions of a file by polling the server. It will only send the deltas or the differences to other nodes in the polling wedge, right? Only if it sees it, right? It doesn't send the entire file, only the deltas. And each new version of a file is given a new version number. And definitely it will share the delta with other nodes in the wedge and also send it back up to the owners. This is not what I'm mentioning here, but this is what is mentioned, what I just mentioned previously, a slide ago. So sometimes it is possible that a node is not in a position to determine if the current version of a site is new or old. So it cannot reliably get a timestamp from the server. Then what it does is it sends the data to the owner, which is supposed to be a repository of all the past versions of the site. So the owner thinks that the timestamp is different, then it assigns a timestamp to the new version of the site and it multicasts it. So essentially the new update flows through the entire DAG. So the owner of the wedge, the original owner, still has a lot of role to play because it kind of owns the DAG, and it also decides if an update is new or not. It does that, and also it propagates the update to all the nodes within the DAG. How does the user interface work? So users need to add Corona simply as a buddy, as a friend in their instant messaging system. Subscribing or unsubscribing to a URL is as simple as just sending a message to Corona. All the subscribed messages are routed to all the nodes in the polling wedge for that particular channel. Whenever an update is detected by the owner of the channel, it is sent to all the subscribers through the IM system. So here polling again is not required. This is kind of like an interrupt driven mechanism where you have consistent connections with the owner of the channel. So this kind of rids the server of maintaining the state. Corona maintains the state like any good content provider. And IM systems will typically allow such kind of a peer-to-peer communication with persistent network connections. Something like what's similar to what Skype does. And so how is this entire system implemented? Well, a standard pastry implementation, 160-bit SHA1. Of course, we have been alluding to the problem that the size of a wedge at the beginning might be 0. Then, of course, we need to adjust the sizes of the clusters or the wedges by just reducing the polling level such that the wedge is not 0. Traditional instant messaging systems like GAME are used to talk to the owner, establish a connection with the owner. So security and trust, well, a lot of emphasis was not given to it. We assume that all the nodes in the Corona system are trusted. And the evaluation, of course, happened on a large cloud of machines on the Planet Lab cloud, where essentially micronews feeds were collected from real-life workloads and the same was simulated on a Corona-based environment. So the system had 1024 nodes, 100,000 channels, So this is kind of a very large system actually. So with 100,000 channels and 1,000 nodes and 5 million subscriptions, this is even much larger than many of the commercial systems that we see. But that was also the aim, to see how much does it scale. The polling interval was set for 30 minutes and the maintenance interval for 1 hour. So every 1 hour there was a reconfiguration, and all the variants were compared: Light, Corona Fast, and Corona Fair. So for all the variants, what we actually get to see is that for the legacy RSS based system, which we are comparing against, the average update detection time, so everything here is measured in seconds. The average update detection time was 900 seconds. With the average load, so let's say the average load, let's look at that in terms of arbitrary units. That was 50. So Corona Light, which of course tries to minimize the update detection time subject to a constraint on the load, so that immediately brought it down to 53. And the load also remained kind of similar to 50. So the aim was never to increase the load beyond what a legacy RSS system would produce. So it brought it down to 48.97 with 53. If I were to compare Corona Fast, which we have argued that it will be faster, so it brought the average update detection time to 32 and the average load to 58.75. So of course Corona Fast is the fastest, and as we can see it is very fast, but it increases the load at the servers, not much though. Corona Fair is something that considers also the rate of change of the content itself. So even with a moderate load, the average update detection time was very high. The reason being that it gives too much of emphasis to the rate of change of content to that time. But once that was kind of tempered down and it was kind of made fair, it was kind of made fair that even slow moving content will at least get some servers. So with this fair regime, with both the square root and the log schemes, the update detection time came roughly to the same ballpark as Corona Light, albeit with much more fairness, and the load also remained very similar to the baseline RSS load. So what we see is that if we are looking at just straightforward update detection time, we go for Corona Fast. If we are looking for fairness as well as a reduction in the server load, the best options are Corona Fair square root and Corona Fair log. So the Corona paper is around 14 years ago. It's a very classic paper, and almost all future pub sub systems have been built on the lines of Corona. So it kind of provided a template for future pub sub systems. It was published in NSTI 2006. Readers are most welcome to read the entire paper and comment about this video.